Welcome to Beyond the Qubit. I'm your host, Frank Dekker. The guest of today is Thomas Ohki. Thomas is the CTO of Emergence Quantum. And I really look forward to interview Thomas because Emergence Quantum is a special company. At the moment, they're not yet relying on external financing. They're funded on customer and partnerships. And Thomas has a lot of experience. He has a long tenure in the quantum industry and he tries to optimize for the long term. And he tries to solve bottlenecks in the quantum value chain. And the specific focus of Emergent Quantum is cryo-CMOS, but they have multiple, they research multiple problems across the value chain. Before we start the podcast, I have an important disclaimer. The podcast is under personal title and I do not represent any company out there. With that, let's get started. Welcome, Thomas. Glad to have you here. Today we have Thomas Ohki, CTO from Emergent Quantum.
Yeah, thank you so much for having me. Nice to meet you, Frank, and I'm looking forward to the show today.
Can you give us an introduction of your background? And maybe as a starting point, can you walk us through your journey into quantum technologies? What sparked your interest first, and how did you arrive your current role?
Right. So you can tell from my accent that I'm in Australia at the moment, but I'm from the US originally. My background has been really, I'm a physicist. I worked after a PhD, for a long time, I worked for a company called Raytheon BBN Technologies, where I led the quantum division there for many years. And then since then, actually moved to Australia, worked for Microsoft Quantum for a little while, and then now started a new chapter, a new company called Emergence Quantum, where I'm co-founder with David Riley, who's a professor at University of Sydney. We started this company, and right now, I'm CTO, CSO of that group. The pathway to quantum is a long one, honestly.
First time that you felt, wow, this is where I want to commit my time and energy.
Right.
To quantum.
Right. So, like I said, I got a degree in physics. I started working on my PhD in physics. Actually, more interested in, quite frankly, high energy physics. I was interested in detector technology and some of the things surrounding that particular area, answering pretty big questions in life, essentially, subatomic particle physics, etc. But I was sitting in a lecture one day in grad school early on and started really getting interested in quantum right at this point where I started hearing about people who were trapping atomic systems. And this is going back to the late 90s or so I'm dating myself. But trapping atomic systems on chips and actually performing quantum experiments with them, using them as quantum systems. People had done this before with gases and atoms and controlling them and putting them in traps with their lasers or other types of things. But this is the first time I've seen that somebody was actually trying to control an atomic system and change its sort of quantum states deterministically, really control it and have it on a silicon chip and move it around, interact with other quantum systems. And it was the fundamentals, it was sort of the basis of trying to do what at the time was called like atom chips and like thinking about computing with that or sensing. To me, it was just, this was like incredible. The fact that you could use atoms in this way has been known. It was something that, I studied, but it wasn't something that really struck me as relevant for technology until I started seeing, well, okay, if you can put it on a chip, then that's starting to become interesting. Maybe you can make something out of it, right? So the more and more I got into this, I started looking into, okay, well, how could I build circuits around that? Started getting into building superconducting films for creating magnetic fields and electric fields for controlling those sort of devices. But then realized, oh, wait, okay, you could potentially make similar things by actually using circuits, different types of junction technologies. At the time, I was looking at superconductors. So I was starting to look at different devices, such as a Josephson junction. It's actually a link between two superconductors and a very, very thin insulating barrier. But there's some really interesting physics transpires from that type of physical system. But what you could do, people were starting to think, is like, oh, you can actually make this into what was called at the time like an artificial atom. Like you create a circuit that could mimic what the energy levels in an atom looks like. So that was another point where I was like, okay, well, that's first of all amazing too, that you could think about how to create a circuit that could behave like an atomic system. But now you married these two worlds together. It's like, okay, I've got a chip. It's much easier to draw a circuit and lithographically design it and make it fabricated on a chip if it's kind of metals rather than putting an atom on there. So this is the point where it spoke to me that, okay, this is going to go somewhere completely different. This technology, taking something so fundamental in science that was, so interesting from a physics level, and then trying to see whether it could be a technology that would be on a normal silicon chip and scale to something that would be potentially useful in computing. That's when things started for me. I was like, this is absolutely something that I have to do, because it was possibly the coolest thing ever that I had seen. So that's the origin of how I got really into quantum, and specifically the path towards quantum computing. At first, it was a novelty to say, oh, you can control them on chip, but thinking about building them in the types of quantum systems to control and how you could actually connect them up and build a computing system out of it was a world that just opened up from there. So that's the origin, and quite frankly, it still keeps me really excited today, that the fact that this is actually true and it works, and where it's gone over the last 2 to 3 decades.
I can imagine. And what did it do to your energy levels?
Well, at that point, I mean, there was no bound to it at that point, because it was almost a completely new frontier. One thing that was interesting about high energy physics, other areas of physics, was that, there's so much known about that area, but it was also a bit of a not disappointing, but at least something that it was hard to find a way to really move forward and do something potentially new or think about it, because somebody has already been looking at that, or many, many thousands of people have been exploring it. But this space was relatively new. So the grounds were not tread upon, and inventing and thinking about new things was almost an everyday occurrence at that point. And seeing a field essentially birthed from the early beginnings was amazing. In that sense, like every time you decided to go back as a grad student and go to sleep, you're wasting time that you could have been actually making progress and inventing a completely new thing. So that was exhilarating. It was exciting to be meeting people who were of the same ilk and cut from the same cloth, that wanted to really forge down a certain path and do something new. So that time was absolutely incredible, actually, from a motivational and energy perspective. And you had to be energized, because the experiments were sometimes, you had to stay up all night and work all night. I can describe a little more about that, but some of it involves babysitting your experiments and staying up all night with liquid helium systems and refilling it at 2 or 3 a.m. in the morning, right? So that was the energy level. Thankfully, at that time I was younger, so it was high and matched my ability to meet my own expectations for how long I could push on something.
Thomas, one of the things that I wonder myself is, what are the benefits that you started so early? Because I think the benefit that I see if you're early on a topic is that you can expand your network and your knowledge level before it becomes a hype. And
Right.
then you're a bit proactive. How did that translate to you? Because you were really early to the topic. And what benefits did it give to you for your network and your knowledge level?
Right. That's a good point. There were several cycles, I think, in quantum application to computing where a hype has been, at different levels, a bit of a roller coaster over time. When I started working in the area, particularly in the area of things that were, say, superconductors, what's called solid state or condensed matter systems, where it's like not atomic systems, but matter that's at least metals and other things that you could pattern devices out of. Those systems were coming of age at that point, and really early demonstrations were being for the first time realized. And there was a bit of an early hype. A lot of people started to get interested in the area, but there was a pretty core group of people that weren't even, I would say at this point, if you see certain people now in the quantum information field, there's certainly evangelists who kind of believe it without too much sort of doubt that it's true. At the time, a lot of people that were in this field, particularly the superconducting folks that I knew, a lot of folks came from nonlinear dynamics and studying chaotic systems and other weird aspects of Josephson junctions. And quantum was kind of well, this is a new thing. Let's see what you could do with it. And it really only over the last, I would say, decade preceding that, was it even shown that these systems behaved in any sort of quantum way. And there was still doubt in that. So there was getting in early, really what it allowed you to do is see all the points of the story, how it evolved into what it was, with a healthy level of skepticism and really kind of due diligence about understanding what's happening. And that colored how you approached most problems, right? Because you came to it with like, okay, you really have to prove without a doubt that this is what we're seeing. So there was a certain amount of rigor that it instilled. With respect to your point about networks, it is interesting because you getting into a field that early, you literally are shoulder to shoulder and went to meetings and had dinner, had wine or whatever with people who were, the parents of the field, effectively, like raising that child from nothing. And so the memories that I have from incredible people over the arc of my career, I've been so lucky to just meet and be around folks who, in their own right, in other fields were huge contributors, but just seeing how that evolved in this particular field and still knowing those people these days and how their role in the community has evolved. Also seeing new generations of physicists and engineers come into the fold has been really kind of exciting and gives me a new appreciation for how mature fields must feel like as you step into them later. Like without that prior knowledge from my own personal experiences, I wouldn't have as much of a deep appreciation or understanding for where we are today and what it took to get there. So that being said, there's always a benefit as far as like, people do say ignorance is bliss. When you know the origin of something, sometimes it may not be great to know that. Sometimes it's better to come in fresh because your ideas are unsullied. So there's there's a give and take there as far as the benefits of having a long history in an area. You don't want to be that physicist who's like, oh, we did that 30 years ago, to all the younger folks that are around you nowadays. I don't think that's welcome. But no, I'm getting to the point where that sometimes does happen. So in any case, that may be a slight negative to the early adoption or the early entrance.
Thomas, you had roles at Microsoft Quantum, at Raytheon. What happened that you said, okay, let's start or co-found or let's work for Emergence Quantum?
Right. So for about 15 years, I was at Raytheon BBN Technologies, and that was a really interesting place for me. That's where I really grew up as a scientist post my graduate and postgraduate stints at Rochester and Chalmers in Europe. I learned really a lot about how professional research was done. In some sense, it was a company, but we weren't producing a product. Actually, the research was kind of a product, so we were working on all sorts of cutting edge technologies. One of them was in the quantum sector. And so we did a lot in computing and sensing. After many years of being there, during COVID, I moved to Australia. I have family that's Australian. And so we tried to actually, it was an unusual time to move, but we did during that time. I led things remotely, which also was sort of only something that could happen during COVID. But went to Microsoft after a bit of time because the pull there was that Microsoft had this really big program that was exploring very specific technology, and it seemed like an interesting opportunity because I came from a background where it wasn't a company that was going to invest a lot of money just in one particular direction for a product, right? We were looking at research. Microsoft was kind of the opposite, investing a lot of time and money into a product. So it was a different way of thinking about it, right? And also was exploring systems that had a nice hybrid of things I was interested as well, superconducting, semiconducting, control systems. David, who is here at University of Sydney, worked with MS for a while, and I knew him from 30 years ago that we essentially were working on projects in a similar direction. So we had always been tracking a little bit the same way as our interest grew in quantum computing. And it was more from the perspective of not necessarily focusing exactly on how do you make the qubits the best as you possibly could, but also how would you grow that beyond what it is, in the early days to, not a few qubits, not even tens of qubits, but thousands, hundreds of thousands. There's some really fascinating problems, and probably both of us were a little bit too early in thinking about those in the maturity of the field, but quite frankly, that shaped how we've been thinking about it and where we are today. And that is a long answer to your question of how we got to emergence, which is we both philosophically felt this was what we were interested in, what we thought from the quantum computing side, our best, focus, or at least our interest would be focused on, the best utility of where, our skills and the group that was massed together and everything sort of seemed to point in that direction of this is the type of technology we should work on, things to help scale. That's really where Emergence is coming from, is that we're a company that wants to do a lot of the research to solve hard problems, kind of the things that I was working on before at the company, like really the bleeding edge problems, things that are a few years down the road as far as we need to implement something to correct now, but also try to do that at a scale of a company which is really accelerating and trying to build towards products. So the fusion of those worlds, where it's engineering and development towards a useful system, but challenging problems that are along the way that need to be tackled, and having a bit of a research but product mindset and building that up, that's kind of the core of where we think Emergence is going, what its strength is, and what we want the company to be known by, and what our mission is. And that is just particularly the quantum computing side. So that's the evolution. That's sort of why we ended up where we are. And in some sense, the start of the company is a perfect combination of all these experiences and sort of the collective growth with the industry over those several decades, kind of like I described before from early adoption.
Okay, that's clear. Thank you. Can you maybe I would love to better understand what are your fundamental beliefs. And typically fundamental beliefs are shaped by lessons from the past. Do you have 3 bottom-up examples that describe lessons that you transferred into beliefs and that can help Emergence Quantum going forward?
Yeah, well, you mentioned 3, right? Or there could be a few. I think one of them that I believe, and I think David, as a co-founder, we believe pretty strongly, is that research isn't just, it's not engineering in our mindset. It's not just executing. There is an element of unknown. There's an element of failure. And accepting both of those aspects as part of the process, incorporating that with an engineering mindset, that experience shapes you to have a belief that you need to understand that failing is actually acceptable in some capacity to make progress. And there's a bit of a, in some worlds, maybe pure product development, that's not necessarily something that's a mindset. And I think that's a belief that both of us share, is that you need to have some of that uncertainty and make mistakes to make progress. So that's why I think we embrace the sector of research that we are. There's an ability to have enough freedom where we can actually move in enough directions to make those mistakes that let you correct in the right way. So without that, I think it's hard to develop technology. So that's one.
Can I give maybe an analogy? I'm a 20-year investor, and some companies are afraid of taking risk. And they have compliance, risk management, and all those functional separations. And everybody's optimizing for its own risk. But if you minimize all the risks, the risk is that you no longer take risk. And if you no longer take risk, then your learning ability is very low.
That's right. Yeah.
I think this feels very similar.
It does. And you see that in lots of different, it manifests in different ways. You can have, your tolerance for technical risk be low. So yeah, it confines you to a direction. And there's a lot of different reasons why it could do that. You need to have structure around anything you're building or engineering. Either it's time, money, resources, whatever. You can't have a million backup plans either. Like, you have to choose. But if things are so constrained that they're moving in a particular direction with little flexibility because you don't want to introduce particularly schedule slip risk. That's one of the big ones in research. And so that one, I think, can constrain you. And being in lots of high pressure government programs, also working in a kind of productization sector for quantum, you saw some of those effects manifest, right? And what it does is it sometimes moves you in a direction it's hard to escape from. Like you may end up in a corner you don't want to, potentially, right? So that happens. There's also other things as far as flexibility of size of companies.
And Thomas, what would be your recommendation for other practitioners in the field? How can you prevent getting into that corner? Do you have recommendations? Because like you, a lot of people will have this issue.
Yeah.
And you experienced it and you learned from it. So what would be your recommendation to the practitioners and listeners to the show?
Yeah. So at least my experience has dictated that, at least to me, that if you adhere to only schedule and you're constrained too much by that and by limited budget, then obviously those are constraints that are hard to live with. You can only think of so many mitigation plans, but typically the way to avoid it and those set of constraints, those are almost unavoidable. You have to be willing to change relatively quickly, and they have to be maybe not even small moves, but large moves, and be able to recognize that and change and adapt appropriately. And so if the organization structure is such that, like you mentioned, if organizationally you've got it structured so you're almost compartmentalizing functions, there's no way to collectively decide to shift. It's organized in a way such that you don't do things like that. You don't move rapidly in a different direction. But I think one way that as a company we survived a lot when I was at BBN was there was a flexibility to go, say you proposed something that was a 5-year project to defense. You had really aggressive goals. It was always a huge thing to have a good enough relationship with the end user or customer where you could go back and say, well, you're managing risk with them, you're understanding how to move forward quickly, you're doing the best you can there, but you have to have the ability to change direction and be straightforward and honest with them about that and how that's going to impact the path, and be able to have that quick feedback loop. The worst thing you possibly can do is just hope you get through it and push through when, the right thing might be to change and have the courage to do so. But have that communication in a tight loop so that you can do that. And so that customer could be anybody. It could be your funding agent. It could be your management. It could be your CEO who has expectations. But that communication, if there's a real desire to succeed, that communication loop has to be present, has to be transparent, and it has to be rapid. So those things, if you don't have that, then you end up in these corners. And sometimes those corners are, in physics language, they can be local minimas that you pop out of, or it could be very stable and you just sit there and you can never get out. So that is probably one bit of advice I would say that I've seen that can be helpful in that.
Thank you, Thomas. I think that's a very helpful example. Do you have other examples of learnings from your career and key beliefs?
Yeah, from a researcher's perspective, also being in a company for most of my career. So I finished a postdoc and then I went straight to a company. What I had experienced was a few different ways that companies went about research. And it's an interesting question or thing to think about. What's the role of a company? Is it to do research, or is it to just productize something and monetize it, make money out of it, right? Those are two different modes of operation, right? So one thing I learned over time was that being part of an organization that valued being at the forefront of research, that's how you got money for contracts, right? Is if you were the one that was clearly at the top of the pile, knew what was coming, the trend, and could execute. And that was the thing that was valued. That actually was the currency you paid in, right? So even if you had larger companies with twice or 10 times the budget, if you didn't stay really at the bleeding edge and really with the top people in that field, you couldn't compete. And it's not only just getting that first contract. Once you get it, or you're working on a project, or you're trying to execute an area, you started falling behind. And the point I'm trying to make is this. The only way to get to the top of any area particularly if you're working in industry environments, is to be reading papers, going to conferences, being in the academic sector, being in places where research is at the forefront, being active in procuring other sort of competitive grants around that area, not just relying on internal company funding to do something, or a pot of money that might be VC, like wherever the funding is coming from. If you're not actually sort of sharpening your skill set while doing that, it's not good for the overall health of you or the business. And so I've seen multiple occasions of this where actually if you back away, like the company I was part of, BBN, it was only 500, 600 people, right? But that company was one of the top defense contractor companies in the US, pulling in many contracts within top 5. And one of the biggest competitors was this company, Raytheon. It's a gigantic monolith. They ended up buying that company because it was such a competitive entity, but it was only 500 people that they could outcompete this huge defense contractor for advanced research technology, right? And so that's a good example that you're keeping, like that company was founded on a bunch of, a lot of academics, a lot of MIT people from down the street. It was in Cambridge and Boston. So there's this startup mentality to that R&D side, and that sort of premise was, staying agile, staying at, up to speed on research, being immersed in not only immersing yourself in what the work is that's pushing technology, but also being part of the community. We would also interact a lot with academic groups, have them as subcontractors on projects, work with them closely. That actually was probably the main reason why we were so competitive, right? So I take that away as a lesson also. As a principle or belief is that in order to be successful, you also, it's not money that makes you successful, or the ability to pull on a large chest. That obviously helps. The hunger and the desire to keep yourself at the forefront and the drive to do that. A little bit of hunger, whether it's like not having a huge amount of resource, is actually helpful, right, to that process. And you can find analogies in life all over the place where that could be true as well. But I won't make those analogies on this. I'll keep it to the science side. But yeah, that's another belief, is that you have to keep hungry, you have to keep on the edge, you have to always be learning. And being competitive with other companies and peers, not hiding things, is one way to keep that edge, right?
Okay, that's very helpful. Maybe let's talk a little bit about Emergence Quantum. How do you describe Emergence Quantum in simple terms to people who don't know Emergence Quantum?
Yeah. We at Emergence are interested in accelerating the future of computing, really beyond where it is today, beyond what you see in AI and data centers. What's the next generation of computing technology? What is beyond that? Whether it's next generations to AI data centers or all the way up to quantum. So the world and its desire for computing is almost unlimited. And so we would like to keep as much pace with that as possible. What the company is doing is we're providing hardware solutions to not only explore, but implement and develop paths towards those next generation platforms. And so one of those areas is quantum computing, because that's one of the really interesting areas that needs a lot of development and is going to take some time, and it's such a complex problem that it's hard not to be fascinated by it. But that's just one sector. We're looking at what comes beyond like the conventional computing systems we have now. It may not be quantum. It likely isn't. I mean, that's usually you don't take a leap that large for a variety of reasons. And there's a whole bunch of solutions, whether it's more energy efficient computing platforms, or where we think cryogenic compute will be in the future of data centers, how that will impact things. And this isn't even related to quantum physics. It's related just to how do we make existing systems more high performance for the amount of watts that you're using. So those areas, that's what the company is looking into, and it's really developing hardware solutions for that. We're looking at new technologies, how new designs of materials, whether it's superconductors for different applications in compute or readout of quantum systems, or it's different modes of operation of silicon technology at cryogenic temperatures. So that's the area that we work in, and we work with a variety of customers in that space, but have an eye on what products will be relevant to the industry and community that Emergence will focus on.
Okay, that's clear. Thank you, Thomas. One of the things when I was researching Emergence Quantums, what struck me is that you resisted venture capital money. Is that correct? And that the funding was more coming from customer engagement and partnerships. So first of all, I want to check, is that correct? And secondly, can you elaborate on that decision? And how does it influence the culture?
Right.
And the atmosphere within Emergent Quantum?
So, first of all, yes, we're not taking venture funding right now. It's not as if we're resisting it, and we do not want to have investment of that sort. It's just we're looking for the right time and when that investment makes sense for the company and at what point in its trajectory. And to understand what that means, maybe we'll give you a sense of why that's the case. And so you would think that, like, why wouldn't you want investment? The company as it stands, what we wanted to do is have as much autonomy as we could on the direction of where we wanted it to go, what technologies we were pursuing, and how we would establish product roadmaps. The thing we didn't want is to have a product roadmap forced upon us because we wanted to make a smart investment decision and turn around a financial gain. So I think both David and I have been around long enough that we knew that we wanted to focus on the technology and its development and its growth and see that growth. So that's one reason. It's not saying that investment of that sort is always only about investment and return, but it does drive behavior in a certain way. And I think we wanted to avoid falling into that.
But for me, Thomas, if you can set up a company, most startups, the biggest problem that they have to solve is, how do we get the capital?
Right. So,
and the companies that are able to bootstrap or start without external capital, that provides you with freedom to set your own agenda, freedom to, and that is really powerful, but it also has a massive impact on the culture.
Yep.
And I think it's a positive impact, because typically I'm an investor in telecom, and the problem is there's too much focus on short-term free cash flow. And if the short-term free cash flow targets are not reached, they do additional cost cutting to meet them. And that is then you create a certain environment of cost cutting that is not the best environment to be on a leading edge or to optimize value. And that can be very negative for the culture of a company. And you're the other way around. So. And I think, but can you explain me, how did you make it possible to start up a company without external capital? Because that's really powerful, and that's really a unique achievement.
Yeah, so I will say this, that there's a bit of a story behind this as well. So I don't know how I don't know how replicatable it is, but. So there's a big team that was part of Microsoft formerly that we decided to start this company and stay in Sydney, Australia. And that was after we were asked to move to US and join the team in Microsoft. But I think we collectively made a decision we wanted to try something new. So there was already sort of a unity in that. So there was a group of founders that essentially said, we're going to stick together and do this. So that's kind of unique. It's plenty, like 20 plus people already to band together and do that. That's not normal. Yeah. Generally. There's also this idea that we are in Australia, and the idea of staying here was something that there was actually a lot of people in the community, up from the government level through administration at the university where we've been, to others across the community, that the amount of support for starting something here and having that process continue to grow and flourish into something like amazing was everybody's hope and desire, right? And so that support is also a little unusual. It can come from a community that's like together, but I came from the US, it's harder to see that happening in the US. It's more of a dog eat dog world. I think less people would care just because there's so many good things happening, and it's hard to say, well, this would be the one that we should really hope happens or materializes. So there's that. The general thing was that in the process of doing that, we like to keep people together while we started raising revenue through contracts and relationships. You needed a way to keep people here. So we all have been part of university as university employees to sort of stay together, stay localized. And as the company's building revenue, what's happening is everybody's being hired into the company, and we build up the revenue to a point where we can stand on our own 2 feet. So that's also a little bit unusual, right? It's not as if, like, most companies will need an immediate cash influx to cover salaries and things like that. So that's a bit of an unusual path, and that's what enabled the original kind of transition, which would have been hard in other cases. Not impossible. I'm saying, like, there's a case where we could have had, like, none of that could have been the case, and we still would have been able to transition. It would have been a lot more sacrifice for some individuals. But the point is that myself and David have had a pretty long track record of being able to work with collaborators, customers, other entities, whether it's government, industry, whatnot, where what we were doing was exactly this, raising funds for the group. So to me, it was actually kind of, it's old hat. It's back to what I was doing at BBN. We were a startup operating in a larger company. And so that model is not unfamiliar as far as bringing in projects to be able to support people. So what we just had to do is do that at a rapid pace. We have a lot of wonderful collaborators and now customers that we call people that we want to start projects with. And I think there's so many things, like in some sense, there's the area we work in, which is, like I mentioned, sort of technology that helps systems scale from the quantum computing side. There's enough people in the community now where their companies or where they are in the technological roadmap, those are things that are really top of mind, right? Where what they need to do next. And I think the last bit, which I didn't mention, is the timing. That's what we're working on actually is relevant at this point. And so it's not just a research curiosity. We've become a part of either, research services, or contracts that we can set up to solve some certain problems, even early product development for solutions for those areas. And so that's also the last part is the timing has been good as far as what we're working on and how that's relevant to the community. So that's how it started, when we're continuing that trajectory. And the hope is that this is how the company is starting. We're building off of that. There's sectors that we're working on that go across not just quantum computing, but like I mentioned, different types of high performance computing sectors as well, where we're looking to expand.
I want to park the topic. I definitely come back on that, because in our investment universe,
right,
we study tectonic changes in compute. Because typically, if you go from the mainframe to the mini computer, to PC, to mobile, to cloud, and now to AI, if you go to the next tectonic shift in compute, the market leader typically increases 100 till 1,000 times, whereas the market increases 10 to 15 times over a period of 10 or 15 years.
Right.
So, but if there's no tectonic shift in compute, then the moats and the competitive advantages are typically higher than people expect. Whereas you see the volatility in the technology stocks, it's quite big. So
right,
quite often the stock drops like 30-40%, whereas if you're able to select the long-term winners and they drop 40%, that's an amazing opportunity.
right.
So that is what we try to study. And that is also one of the reasons why I started a podcast. Because early in the process, I want to build my knowledge and my network.
Right. Yeah.
But sorry for that, but let's park it. But
it's fascinating.
I'm all on your ears on that topic. But maybe first, what is the mission of Emergent Quantum? We touched already a little bit on it, but maybe 1 or 2 sentence summary.
Yeah. So, I mean, our mission is to become an R&D company. That's the main core. But also to build parts of the company that can spin out other technologies into products. Still have that core R&D business that feeds those other wings. be contributing across all those platforms that I mentioned in quantum computing, sensing systems, and energy efficient compute. I think that the ceiling is very, very high as far as what we could do and how large we could grow. And that's largely dependent on, I think, where we're satisfied. I think David and I, we've seen where things could go. At this moment, we're not putting our cap on things as far as the type of entity we could grow into. Given what we're working on, the sectors we're in, I think that allows us that growth opportunity.
Thomas, can you explain in basic terms how your technology works?
Yeah, so there's three sectors that we're in. Like I mentioned, quantum computing, sensing systems, and energy efficient compute. There's a horizontal across that, and that horizontal technology is right now a lot of technology that for certain systems forms different purposes, but it's based on a lot of cryogenic electronics that's used for control and readout or energy efficient compute. But it's based on silicon CMOS technology, other 3-5 materials for different types of devices there, superconducting materials for not only RF components and logic, but these kind of discrete technologies for these functions, most often sitting in some low temperature environment because that's where we've kind of optimized the technology. And the role we play is, you can imagine, a lot of technology may sit at very low temperatures, and then you have things that obviously wouldn't be at low temperature. We form sort of the
Thomas,
connective
maybe
tissue between those layers. Right, so
clarification, if you talk about low temperature, what do you talk about? Do you talk about 4 millikelvin temperature or 200 millikelvin? And what is the difference for somebody who's not familiar with millikelvin temperature? What is the difference between 4 millikelvin temperature and 200 millikelvin temperature?
Right. So I said low temperature because I didn't want to distinguish a particular temperature. Depending on which application you're in, if you're in quantum systems, sometimes you need very, very low temperature. So you're talking about 4 millikelvin, like you mentioned. Those are temperatures where what you're trying to do in certain systems is remove any sort of thermal effects in your system, any noise that's from heat. And so we don't need to go that low in temperature for certain applications. In quantum, very lowest temperatures are, down to that degree. If you multiply that by 2 orders of magnitude, there's certain other qubit platforms that function at 400 millikelvin, even some that are above 1 Kelvin. There's a continuous spectrum of temperature where performance of things can be kind of optimized. So rather than sort of say to somebody, what does that temperature mean? I would say that if you looked at a graph and plotted different sort of applications on that and what starts to turn on as a function of temperature, if you start at room temperature, that's your conventional kind of computing technology. If you go down a little bit further, maybe liquid nitrogen, that's 77 Kelvin. Still pretty cold, but people have already done a lot of analysis that says, actually, at that temperature, CMOS is optimal for a bunch of different reasons. It just hasn't been like overly explored or built at that temperature. But as you go even lower in temperature, different effects turn on. Like if you go down to a few Kelvin, like basically another factor of 10 from liquid nitrogen, you start to see different things, like superconductivity comes in. And then it opens up a whole nother range of technology. If you go another order of magnitude, or another factor of 10, or another factor of 100, then you start to see quantum effects. And so it's rather, instead of say, what's the difference between 4 and 200, this spectrum of temperature, you can think of it as these interesting physical effects start to manifest the lower and lower you go. And our mission is trying to take advantage of some of those technologies, and where on that line you sit, sort of, it depends on, for instance, how good do you want that system to be? How good of a computer do you want? Like how much error can you tolerate? Or like, is the system even possible to build? Because it's not easy to build these refrigerators, right? And somebody wise always told me, if you can't build something that's at least 10x better than what's your competitor, and it requires you to cool it down, then forget it. There's no point in doing it. And so that rule usually holds true. I mean, it's not a completely in stone thing, but there is a cost associated with cooling. But this is kind of an interesting point for other technologies. I won't get into that right now at this point. But that's generally, hopefully, an answer to your question.
Yes. But then coming back, you said, okay, we have 3 products: quantum computing, sensing, and high performance compute. Is that correct? And
Yeah.
then you said we try to. So my question was, how does your technology work?
Yeah.
Could you summarize that? So
the technology, how does it work, right? So it's not too different than normal digital or analog electronics. So all it is electronics that enable you to either measure a quantum system or dissipate less energy, be more efficient in computing. But if it's a transistor, it's still a transistor at low temperature. If it's a superconductor, it's, it still has its superconducting effect, so it doesn't act in a different way. What we're actually doing is enabling it to perform a function, rather than saying, this isn't us saying we're creating a new material that does this brand new property or does this new bit of physics. It's actually, there's some pretty well-known things that people have done for many decades, but engineering that, understanding some of the physics ramifications for building that hardware, particularly like things like operating semiconductor technology at millikelvins or Kelvin temperatures, low temperatures, requires you to engineer it a little bit different. You have to change the devices a bit. So it's not that it's functioning differently, to your point, but it's just more optimal for the environment that it's in. So I'm not sure if that helps a little bit.
Yes, now what pops up in my head is, yes, what are the difference between normal semiconductors and semiconductors for quantum? And I think, yeah, you have superposition and you have entanglement, and because of that, those constraints, you can use different materials and you could operate in a different environment, depending on which quantum technology you use.
That's right. Yeah. So there's one interesting thing is to expand upon what you're going with here as far as a thread. There are a variety of technological platforms that could be quantum in nature. A lot of them are operating at a low temperature now. So we can think of those as the quantum layer. As you move up in a system, there's other things that do the signal delivery or signal retrieval of that system. There's always an I/O to that quantum layer. A lot of that technology.
Recently, I interviewed Delft Circuits.
Right.
The CEO, and they did the cryogenic cables.
Right.
Output.
So that the I/O, the physical I/O is one challenge. The active components that provide signals is another challenge. Where does that sit in your system? Each qubit or quantum system has its own requirements. What I'll say is this, in really, really broad terms, this layer that we provide between, say, a user that wants to interface a system that comes to a room temperature system, types in a set of commands, runs an algorithm that then compiles down to instructions that goes down to a processor level at the quantum level. There's a whole bunch between those two things. Like there's a huge amount of engineering between those two functions, right? So what is kind of a subtlety is that what our technology really does is bridge the worlds of what you would call kind of classical systems or electronic noisy things that are, higher temperature, room temperature, things that wouldn't observe any quantum effects, and connecting those things to these quantum systems. And the quantum systems are very fragile, very delicate, can be destroyed by the smallest amounts of noise. Connecting those worlds up is not as simple as just taking two things and putting them together. You need this interface layer that is designed in a way that it's not just engineering for low temperature. It's actually engineering with an idea that you're connecting this really delicate system to this other thing that's almost like, could be the temperature of the sun if you really thought about it. They're so different in scales of energy or in the noise. Bridging that gap and still making that whole system work, that's kind of the beauty of this whole challenge. That's how this field is going to end up evolving and working in the end of the day, is whoever is successful at doing that the best and in the smartest way to make big enough systems, that's how you end up winning this.
And Thomas, can we maybe take one step back? Where do you sit in the quantum value chain? And who is your closest comparable? I interviewed, for example, Q Blocks.
Right.
Who does the who does the control systems. I interviewed Delft Circuits.
Right.
Who does the input-output, chirogenic cables? Where do you sit in that value chain?
Yeah, so that's a good question. So there's people that develop typically electronics that's room temperature that interfaces through, at this moment, already pretty dense I/O that goes down into maybe fridges or some cryostat. It depends on what system you're working with, but all of them kind of at this point do live in some cryogenic system. So
And I
except for a
think
few.
that is the Q blocks. Q blocks has controlware.
Yep, and then
But
we kind of sit in a layer below that, where at some point in time systems get big enough that you can't imagine that everything is going to be sort of discrete components outside of your system as you sort of deal with the ingress-egress problem of going to a quantum layer. It'll be a
Thomas,
much more engineered solution across the stack.
What do you mean of that? Do you mean if you say the system gets bigger, do you mean that the fridge gets bigger? and that you have to be, the control elements have to be inside the fridge? Or what exactly do you mean? I don't understand it. Could you explain that to me? What do you mean with the system and what is actually getting bigger?
Right. So in certain circumstances, the scale at which a quantum processor grows could be a variety of different platforms. It starts to become more and more difficult to think about the I/O density out from those planes and going through discrete wiring cables all the way through meters of cables to other control systems.
Is this if I compare it with AI, is it like the scale up? So what you see now with NVIDIA, they have NVLink 72. They connect 72 GPUs in a rack, and then they have scale out. And with scale out, they connect the racks. But the scale up is done with copper, because there's no active signal on it. Because if you put the active signal on it, then it requires much more energy.
Right.
And they want to stay as long as possible with copper, unless that's no longer possible if you scale it up. But they're from 72 GPUs connected, the next step is they're going to connect it with 4,000 GPUs, but it's going to be with co-packet optics. So they move to light, but then the energy equation totally looks different. But what do you mean? So if you say we scale up the system, do you have an analogy like scale up and scale out? And scale out is connecting the clusters.
Yep. So scale up is what I'm primarily referring to. So in a, say, single compute platform, the equivalent of a blade, you'll have maybe multiple quantum processing units equivalent to your multiple GPUs. Maybe they'll be stacked or on other types of arrangements where you start to increase the I/O density dramatically at that plane. At that point, you could either take lines and fan out and then keep fanning out to the point where you get to discrete components outside that do control of the system, or you keep it where you're doing lithographically defined connections, or keep it in a nearby or co-located near the processing units, right? And so that your fan out is not as severe. There's fabrication challenges. It really depends also on what technology you're talking about. Like for instance, semiconductor qubits, they have a very small footprint. It's challenging as far as the fan out to other circuitry. So a lot of the effort is to think about how to bring local control to those technologies in particular. So you'd want to have high density control units that are providing signals that are proximal to your device, to your quantum processor, not pulling it out at any level. So we're not even talking about scale out. It's more, or connecting of computing units. This is really at what the people have been calling the quantum processing unit, like the equivalent of your GPU, right? So your primary processing unit. So some technologies are like that. Some, as the number of qubits
helpful,
grows.
Thomas. Thank you.
Yeah, no problem.
Thank you for explaining the basic concepts to me, which I'm not familiar yet with.
Yeah, no, there's similarities to the data center analogies. There's an energy optimization that's always there, when to keep signals in certain wires because there's a lower energy cost to doing so. That exact argument can be made for a lot of the same types of architectures for quantum computing systems. So you're bringing up a very valid point. Like you have to do sort of a full trade study of what does your quantum processor require as far as clock frequencies, IO density, number of signals. Look at the requirements of the circuits that are driving that. Look at the power that you're dissipating over the channels that you have and the bandwidth of those channels. It's very much the same types of arguments. Like people also are thinking about when to move to optical to sort of gang systems together and scale out. So the same optimization is true. So that's what I mean, scale out. And you mentioned Qblocks or quantum machines or other vendors. There will be a challenge as the quantum processor densities and the number grow in a single system that fan out to the systems that are at room temperature will become more and more challenging. And there's some platforms, like I mentioned, that natively want to, as the system size grows at the processor unit, you'll have to be closer to that processor, or even in some cases co-located nearby, even
And can you also
flip-chipped.
design it on chip?
In some technologies, yes.
What are the pros and cons of doing that?
Well, so I've seen the spectrum of quantum devices from, say, superconductors. If you talk to companies building those systems, they'll be extremely hesitant of putting any active circuitry near the processor layer because we've spent many years shielding it from that. So it's almost a no-go to think about that, to do anything monolithic. With other systems, like for instance, semiconductor systems, they're much more robust against thermal effects, other things that would normally harm, say, superconductors. So you can almost have them monolithic. And in some cases, that's some people's roadmap. In other cases, it's not directly controlling your single bit or anything like that. But for instance, ion trap systems, for a long time, people have been developing traps to shuttle ions around a surface to have them interact. That's their computing platform. Control electronics people have been trying to engineer monolithic control for the electrodes that actually move these ions around. And so there's a vision for all of these platforms to some degree. Each one has a different need, but a lot of them do have this requirement that there's really tight integration. It could be exactly this, monolithic or backside processing of subs and other versions of that where it's a little bit more distributed.
Okay. Thank you.